Okay, so we're going to prove that 1 squared plus 2 squared plus 3 squared plus 4 squared all the way up to plus n squared is equal to a sixth n multiplied by m plus 1 multiplied by 2m plus 1. We do this by induction. Okay. Now the first thing to do is we're going to, this sum here is a bit long. We don't want to have to write our sums like this all the time, because otherwise we're just going to be writing massive long lists. We're going to write this using sum notation. Now what is the symbol we use for if we're adding up things? Really good.
Sigma.
Sigma. Can you do it with your big hand?
It's like a weirdie.
Yeah. Okay. So this is basically sigma. Okay. We're going to prove that the sum, now here it starts with 1 and it goes up to n. Now we're summing up all of the square numbers. And what I'm going to use is I'm going to use the letter R to denote a generic square number. Okay, so we're going to add up all of the square numbers from 1 to n. And we're trying to prove that this is equal to a sixth n, n plus 1, 2n plus 1. Okay, that's what we're trying to prove. Now the proof by induction always follows 3 steps. Okay, first of all, okay, first step we are going to prove the base, what we call the base case. So we're going to prove that the first domino falls over, and that's when n is equal to 1. We prove the base case n is equal to 1. Now this is really easy because the sum of 1 to 1 of r squared is just 1 squared. We're just summing one square number, so that's equal to 1. And the formula also gives us, which is sixth, n plus 1, 2n plus 1 is equal to a sixth of 1 times 2 times 3, which is also equal to 1. These two are the same. The case when n is equal to 1 is true. This is incredibly important. It seems trivial, and it is trivial. It's not difficult to prove at all that when n is 1, the formula works, but it is fundamental for the proof. There's a lot of really good inductive proofs, some really clever ones, but they're not proofs unless you have proved the base case. It is a really common mistake for students to forget to prove that base case. You really need to prove that is the first thing you do, and you'll get marks in the exam, even if you don't go any further. Just by having the n equals 1, you get marks. It's really important. Okay? Now, step 2 is what I call the inductive step. Okay? And this is where it gets tricky. We have to assume the theory is true, assume the formula is true for a particular value of n, and we usually denote it by k. Okay, so we can assume that it's true that n is equal to k. So that tells us that the sum from 1, and in this case k, because when n is k, we're saying it's definitely true. We're assuming that it's true. Of r squared, now that's going to be equal to, if we put k into the formula, a sixth of k, k plus 1, 2k plus 1. Okay, we are assuming that this you can put it in yellow. We're assuming that this formula is true. It's true for this particular value. Okay. Now, how I do this is then right at the bottom of my page, I write what I'm trying to prove. Because this is true. What I'm going to try and prove now, and this is the inductive step, that the formula is also true that n equals k plus 1. Okay? So I like to have a little target in mind. And I know that my target is that the sum from 1 to k plus 1 of r squared is equal to, well, it's going to be whatever's up here, but we're going to replace k by k plus 1. So it's a sixth k plus 1 k plus 2 multiplied by, now 2 lots of k plus 1 plus 1 is going to be 2k lots plus 3. This is what we're trying to prove. This is our target. As soon as we get this, we know we've proved it. Okay? This is the statement. The green statement here is the statement for the yellow statement is the statement for. We'll highlight that in red instead. More lessons on this. The yellow statement at the top is what we're saying is true. The statement in red at the bottom, which I've circled, is what we're trying to prove. Okay? And this is the case when n is k plus 1. So, unfortunately, we have to start here. Now, what the sum of this is the sum of all the square numbers up to k, the kth square number. Okay? So I could write this, you don't necessarily have to write this each time, but you could write this as 1 plus 2 plus ... plus k minus 1 all squared plus k squared. Okay? And that's what we're saying, that is definitely equal to a sixth of k, k plus 1, 2k plus 1. Now, I'm looking at my target at the bottom here, and I want the sum of all the k plus 1 square numbers. Now here, I've got the sum of k square numbers. What can I add to this so that on the left-hand side, it becomes the sum from 1 to k plus 1 of r squared, Sam?
Square of k plus 1?
Yes. If we add, so here we have k minus 1 all squared plus k squared plus k plus 1 all squared, suddenly this sum here looks exactly this sum here on the left hand side is exactly the same as the left hand side of our target. Okay? I've added the k plus 1 square number. But we don't know that. We use the first line, and we have to treat this like any other equation. Whatever we do to one side, we do to the other. So this becomes a sixth k, k plus 1, 2k plus 1, plus k plus 1 all squared. Okay? Too many k's. Special k. What?
Not one of the best ones.
Not one of the best ones. Shame. It's being recorded as well. Never mind. Right. Now, as I said, this here, just highlighted in yellow, this is exactly the same as this here. So this, brilliant, we've got the sum from 1 to k plus 1 of r squared. Brilliant, we've got the left-hand side sorted. We have got to prove now that this right-hand side is the same as a sixth k plus 1, k plus 2, 2k plus 3. Now, this is where your algebraic manipulation skills are going to be, they're really going to be tested. They're really going to be tested here. We've got two terms. We've got this 6k plus 1, 2k plus 1, and we've got this k plus 1 all squared. What might we factor? Can we factorize out anything there? Go on, Mez. Yeah, we've got a k plus 1 in both terms. Okay. Now the trouble is, at the bottom, we want a sixth all factorized out as well. So I'm going to factorize out a sixth k plus 1. Okay, and that gives me my first bit there. And you're thinking to yourself, well, there isn't a sixth with that k plus 1 squared. That's not a problem. We can still fiddle it a bit. So we've got a sixth k plus 1, and then I'm going to introduce these square brackets, which unfortunately because of a malfunction in the board, they're a bit on the hook. That's a classic Norfolk phrase for anyone watching. So to get this term here, we have to multiply by 2k plus 1. That is really irritating. I think we can just about see that as 2k plus 1. And what do we multiply to get k plus 1 squared? What do we multiply this by? We've got a sixth k plus 1 multiplied by, gone? 6k plus 1. Okay? 6k plus 1 multiplied by 6k plus 1 becomes the k plus 1 squared. So that's how I've kind of fiddled that. If we multiplied that to that, we'd get that. If we multiplied that to that, we'd get that. Okay? Now, we've got 6k plus 1, and in square brackets we've got 2k plus 1. Well, what have we got? We've got
You showed K on something like
I should have a k there, shouldn't I? This spot. There's a k there. I lost that k somewhere. I was going to say I was. Yeah, so I lost my k, which was there in the second line to there. So what do we get here? We get 2k squared plus k. But we've also got 6k, so this is plus 7k. And we've also got plus 6. Okay, just by tidying up what's inside those square brackets. What we'll do, we'll move our target a bit down. What are you saying then? Is it Jack? Brilliant. Yeah, we factor out, because we know what the target is, this has got factorised to that. And it blinking well does, doesn't it? This definitely factorises to that. So now, because we're clever and we've got our target, we can say, okay, that's k plus 1, that's k plus 2 multiplied by 2k plus 3. Oh, hello. Same as what we wanted to try and prove. We are done. End of proof. We have proved that if n is k is true, then n equals k plus 1 must also be true. We also proved n equals 1 is true. Therefore, n equals 2 has to be true. Because n equals 2 is true, n is 3 is true. Because n is 3 is true, n is 4 is true. And so on and so forth. All the dominoes fall down. All the dominoes fall down. Because we have proved that if it's true for n equals k, this formula here, by using some algebra, we have proved that it's also true for when n equals k plus 1. This one here. And once we've done that, and we've proved that it's true for n equals 1, that forms our proof by induction.